Welcome back to Math 104. By the second approach to computing expected value, the expected number of wins in three plays of the game equals the value of the following sum: number of wins times probability of that many wins, plus number of wins times probability of that many wins, etc., through all the different possible numbers of wins. So 0 wins times the probability of 0 wins, plus 1 win times the probability of 1 win, plus 2 wins times the probability of 2 wins, plus 3 wins times the probability of 3 wins. You could work these fractions out exactly, or you could just use the calculator and compute them in decimal form. They work out approximately to the following: 0 wins times a fairly large probability. It is more likely than not, in 3 plays of the game, in 3 rolls of the dice, that you will get 0 wins. There is almost a 64% chance that you will end up with 0 wins. There is almost a 31% chance that you will end up with 1 win. Well, between 0 wins and 1 win, that's almost all the likelihood. That's almost 95%. There's a nearly 5% chance that you'll get 2 wins, and almost no chance at all that you'll win all 3 times. So what we're doing is we're taking each number of wins and weighting it by its probability. When you compute this weighted sum, this weighted average, you get what turns out to be exactly 5/12ths, if you work with the fractions here, or approximately 0.4167 wins. This 0.4167 is not a probability. Although it's a number between 0 and 1, it is not a probability. It is an expected number of wins. It is a long-term average number of wins in 3 plays of the game. Now, suppose you hear someone say that the possible number of wins in 3 plays of the game is 0, 1, 2, or 3 wins. Okay, that's perfectly correct so far. The person goes on to say that the expected number of wins in 3 plays of the game means the same thing as the long-term average number of wins in 3 plays of the game. If the experiment is to play 3 times, and you repeat that experiment of playing 3 times over and over again, in the long term, there is some average number of wins, and that's what we're looking for. That's what we mean by the expected number of wins. That statement is also true. Now the person goes on to say that therefore the expected number of wins is just the average, the ordinary average of 0, 1, 2, and 3. You add them up, divide by how many numbers there are, and that would be 1.5 wins. So think, what is wrong with this argument? This is a common error, by the way. So think, what is wrong with this argument? Pause the video for a moment and try to formulate why this is incorrect. The key point here is that the expected number of wins really has to be a weighted average. Each number of wins has to be weighted by its probability, otherwise there's nothing in this computation that would reflect the fact that 0 wins is much more likely than 1 win, and 1 win is much more likely than 2 wins, and they're all vastly more likely than 3 wins. That information is relevant to what happens in the long run, so our computation has to know about that information. A computation that omitted that information could not be correct. So this computation uses our second method for computing expected value. Our second method is the one that does not involve ideal datasets, but instead computes expected value as a weighted average of the values that can be achieved in the experiment. Each value weighted by its probability. Now if 0 wins, 1 win, 2 wins, and 3 wins were all equally likely to one another, then they would each have probability 1/4, or 0.25, and then we'd be weighting each one by 0.25. Then you really would end up with 1.5 wins. That's a way that the hypothetical person we were just talking about could come up with the correct answer, but it could only be correct if 0, 1, 2, and 3 wins were all equally likely to one another. Another way of saying that is that the mistaken computation of just averaging up the numbers 0, 1, 2, and 3, and obtaining 1.5 as their average, would have been correct if this 0, 1, 2, 3, one copy of each number, had been an ideal data set of the number of wins in 3 plays of the game. As I like to say it, this computation was the incorrect approach to our question, but it was the correct approach, the correct answer to a different question. We've seen a correct application of our second method of computing expected value to this game. We can ask, how could we use our first method for computing expected value? By finding the average of an ideal data set of values. If we apply it correctly, this is guaranteed to give the same answer as the second method, but it involves a different way of thinking, and it's worth understanding both of them. In this example, it is a bit harder to find the right size for the ideal data set, so I will just tell you what it is, and that is that 36 times 36 times 36 outcomes, which is 46,656 outcomes, will work. It will work as the size of an ideal data set for the experiment of playing the game 3 times. How did I come up with 36 times 36 times 36? If you look at the probabilities that we were just computing, they involved something over 36 to a power times something over 36 to a power, and those powers added up to 3. So you'll get a big denominator with 36 times 36 times 36 in it. If you take a fraction where this is the denominator, and multiply it by this number, the result will be a whole number. Let's look at what this means concretely. There is a set of 46,656 numbers, consisting of a certain number of zeros, a certain number of ones, a certain number of twos, and a certain number of threes. The relative frequency of the zeros in this large set is equal to the probability of 0 wins in 3 plays of the game. Since the probability of getting 0 wins is so high, very many of these 46,000-something numbers are going to be zeros. Similarly, whatever the probability is of getting 1 win in 3 plays of the game, that will be the relative frequency of ones among these many numbers. Similarly for 2 wins, and similarly for 3 wins. This is meant to refresh our memory about what an ideal data set really is. I encourage you not to be intimidated by the size of this number here. Just go back and think, what does ideal data set mean? The relative frequency of each number in that set is the probability that that number occurs when you run the experiment. And the whole reason why we talked about ideal data sets was to be able to say very concretely what expected value means. The expected number of wins is concretely just the average of this set of 46,656 numbers. There are a bunch of zeros, ones, twos, and threes, and when you average up this large set of them, you'll get some number. Before going on to the next video, find the number of zeros, the number of ones, the number of twos, and the number of threes in an ideal data set of 46,656 numbers of wins in this experiment, and then compute the expected number of wins in this game by finding the average number of wins in the ideal data set. You should get the same number we computed earlier, 5/12ths, but this is a different way of thinking about it and a different way of computing it.